Okay, so we've been doing area between curves. Now we're going to take it up a notch and do something crazy, and we're going to find volumes of some weird shapes. And we're going to create these weird shapes by rotating a normal shape that we've been finding the area of. We're going to rotate it around the x-axis faster and faster and faster until it kind of makes a solid. So we are going to make a bunch of disks. Imagine, and this is weird at first, but imagine I had an equation that looked like this. Boom. Okay, area trapped under the curve. If I took that shape and I rotated around the x-axis, imagine it coming out of the paper at me, going back down in, spinning around faster and faster and faster, like it's on a lathe. Basically, it would make this shape mirror image of itself, but it would be 3D, so it would come out of the page too. So if you thought about it, I'm going to give it a little dimension. Ooh. Right? So you can imagine it sort of looks like, I don't know, a clove of garlic. I don't know what else to call this. I've seen some ornaments on a Christmas tree like it, right? So if I looked at a little slice of it, it would be 3D and it would make a disc, right? If I took little tiny slices, remember how we talked about rectangles? And if you had rectangles, you could approximate the area and get closer and closer. Well, this method is called the disc method because if you look at any slice on here, it is a disc. And guess what? This is the width of the disc, and the radius is there. Well, guess how you find the volume of a disc? The volume of a disc is pi r squared times width. Okay, well, what's kind of cool is as you get tinier and tinier and tinier and tinier little slices, because we're trying to get exact, we can change that into the width into change in x, or delta x, how tiny it gets. It's so small we don't even have a width to it, and we call it delta x. So if that's the volume of one disk, the volume of a bunch of disks can be written like this. It's the sum from 1 to n of pi r squared times width. You're just doing a disk and a disk and a disk, however many disks you have. Well, if you want to take that to the extreme for an exact area or volume, we don't have to have the sum of a bunch of disks. We can actually get the integral from a to b. Now I could do pi r squared, but guess what my radius is? My radius is the y value, or f of x. Because if this is f of x, and then I need to square it, because it's pi radius squared. My radius at any time is the height of this function. See that? The radius of this disk is height, radius of this disk is height, it just spins around. So instead of a width, we're going to say dx. So one of the cool things about any constant inside, we learned this rule a while ago, you can pull a constant out. So basically, remember all that stuff we did before for doing integrals? It's pretty much the same thing, except you have to do your radius squared, or your function squared, and then times pi at the end. And the whole reason, this is the new formula. The new formula right here, this is the one you're going to use a lot today. It's going to get weirder in the future, but if you spin around the x-axis, you can kind of forget all this other stuff. It's adding up a bunch of disks, and if you want the exact area of this weird ornament shape, it's kind of like a teardrop or a lemon drop, you do pi, the integral from a to b, that's the starting point a, the ending point b, of f of x squared dx, and then times pi. So let's try this with a shape that we can do. And you'll see these problems are actually easy if you just use the formula. If you're good at the old stuff, it seems crazy that we can find the volume trapped by this thing in the x-axis. Later on we'll do a different axis and you'll see. So here's our function. Radical 3x minus x squared. Okay, so we always want to look at a graph of these. Okay, so if I look at a graph of this guy, starts at 0, goes to 3. You could zoom in a little, maybe zoom box. I like zoom box if you've never used it before. Life changing. You hit enter on a corner, drag it over with your cursor, and it, whatever your box is, becomes your new window. Okay, so here's my equation. Goes from 0 to 3. It's like a, I don't know, not a circle. It's more like an oval. Okay, so 1, 2, 3 starts here. It's hard to tell what the height is, but it looks like 1.5 maybe. Okay, so it's going to go boom. Okay, so it's like a half an oval. Okay, now we're going to rotate this about the x-axis. So I draw this, and it comes out of the paper, and then it goes back in the paper. Basically, it makes this football shape, right? More like a rugby ball. They're a little fatter. I always like to draw one disc just to show its 3D-ness, its dimension. So we draw a disc, and you look at that, you're like, oh, it's a rugby ball. Okay. Now, you'll see how easy these problems are. As long as you know I have a 3D shape, I'm rotating around the x-axis, I know my equation, I just have to go the pi times the integral from, remember it's your x's, 0 to 3. Oh shoot, I missed 3. Oops. Pretend that hit at 3. I think I went out to 4. From 0 to 3 of my function squared. Well, this is going to actually turn out nicely. You might have been freaking out a little that it was a square root, but you got to square it anyway. What happens when you square square root? It gets rid of the radical. That's actually the best thing, is if you have a square root problem. So the volume of this crazy shape is whatever your answer is from 0 to 3 integral times pi. And remember how to do that. You take the exponent up 1, divide by the new exponent. Take the exponent up 1, divide by the new exponent. Evaluate from 0 to 3. So we're going to plug a 3 in once. Remember, you're going to do pi at the end. Okay, so when I plug the 3 in, it's 3 times 3 squared over 2 minus 3 cubed over 3 minus 0. Actually, you've probably done enough of these that you know that's 0 and that's 0. Okay, so all I really got to do is carefully type this in. 3 times 3 squared. Oops. Oh no. Oh no. I said carefully. 3 times 3 squared over 2. I'm going to pause it while I do this so I don't waste time. Alright, so we got 3 times 3 squared over 2 minus 3 cubed over 3, and then minus 0, and then that's 4.5. 4.5 pi, or, so we're going to multiply by pi. Oops. And I get 14.14 units cubed. That's the volume. That's the volume of that weird football-like shape. Okay, so this isn't that hard. You gotta get used to it. So that's called the disk method. Let's see. So maybe let's try another one. Let's try something different, like. Okay. Okay, let's try, this is another disk method, and then I'm going to show you a different one that's called a washer method. That's kind of sneaky. Okay, it depends if there's a hole or not. If you noticed, this shape was solid, no holes in it. So every piece I took was a solid disk. You'll see in the, not this example, but I'll do one more example in a different video and see. Okay, so we're going to say our equation is going to be y, or f of x equals, let's go with 3x plus 1. Okay, so this looks pretty nice, right? If you looked at a graph, you know what this looks like. You start up 1, then you go up 1, 2, 3, right 1, right? 1, 2, 3, right 1. Okay, let's do that. Let's say I want the area of this shape bounded by this guy and the line x equals 2 and x equals 0. So sometimes you get more things. So basically I'm telling you where to trap this curve. And y equals 0. So bounded by. So basically we're taking this shape here and we're spinning it around the x-axis. Okay, so we're going to spin this around the x-axis. Well, what's it look like when it goes around the x-axis? Well, it just looks like a mirror image, right? So you're going to have this shape here. And to give it a little roundness to it, it might help you to, on the end, kind of draw an oval. And on this end. So kind of see that? Looks like one of those cones you would put your dog's head in if they had surgery, except it's solid. So whatever the solid version of a cone is. So I think there's a candy that's shaped like that, right? So imagine this whole thing. If I took a slice out of it, it would be a solid disc. There's no holes in this. So I'd have a solid disc there. Basically, what am I going to do? I'm going to say I want the volume equals pi from 0 to 2 of my equation squared. Now is when you got to do a little more work. This previous problem looked worse, but when you square a square root, it's done. When you square this thing, you have to think that's 3x plus 1 times 3x plus 1, right? So you're going to have pi from 0 to 2 of, and if I FOIL this out, you're going to have 9x squared plus 3x plus 3x plus 1, right? Sometimes you got to go through the squaring process. But after you do that, is it really hard to do the integral? No. All you got to remember is your pi and your squared, and these problems are pretty easy. So you're going to go 9x cubed over 3, raise the power up, divide by the new one, 6x squared over 2, and x from 0 to 2. Okay, almost there. This simplifies. I kind of want to rewrite this. That's 3x cubed plus 3x squared plus x. Now I'm going to plug in a 2 and a 0. And don't forget your pi. A lot of people forget pi. It's an easy thing to forget. Don't worry, back here the 0 plug-in part is just 0. The front plug-in part is 3 times 2 cubed plus 3 times 2 squared plus 2. I'm plugging in a 2 everywhere there's an x. Then I plug in a 0 everywhere there's an x. It comes out to 0. Alright, so I'm going to pause, do that real quick. Okay, I did all that and I got 38. So 38 pi, and that's the volume, but I always like to know the actual number. So I do 38 times pi, and we get 119.38 units cubed is my volume of this crazy shape, the solid dog cone. So that's pretty crazy. I'll come back in the other video and show you what you do if it has a hole in it, because this is solid, and this was a solid football, right? It's a solid cone-like shape, solid football. So you have to treat the problem a little differently if there's a hole in it. These two are called disc method because every time I took a slice, it was a solid disc. If you, the other method's called a donut method if you have Mr. Hewland, or it's called a washer method in most books. All right, I'll come back for one more example.